Okay, so let's start. Today's speaker, Lubomir, our first international speaker outside Brazil, is going to talk about perturbation theory of quadratic isochronous systems revisited.
Yeah, okay, thank you. So the talk is about how to say, not a general theory, but the opposite of a general theory. So about a particular case, a particular differential system on the plane. This is the system that you see here in Formula 1, which of course we are not so interested in this system, but it is rather beautiful. We shall see why. But of course, the reason is that we are looking for some general theory, and this is a good example to illustrate, to show what is the general approach to a more general theory. So this system has a long story, more than 50 years, and it is known to have two centers. So it is integrable one, it has a first integral, and the particularity is that this is isochronous. It means that the period of each orbit is constant. So you have two centers with infinitely many orbits, and the period is constant, which is more or less obvious if you write down this system in complex coordinates. As you see in Formula 2, what does it mean? It means that, the initial system is real one. Let us cheat a little bit and put z equal to x plus I y. So identify the real two plane with the complex plane, with the complex one-dimensional complex plane. And then you get these differential equations, which is holomorphic one. And as every holomorphic equation, it should have, it should have a constant constant period by Cauchy theorem. Okay, so the first integral, you see it here. It is written down. So it is almost trivial, not completely, but okay. So it's a rational function, and of course, all this induces a complex foliation. In fact, vibration, because we have a first integral, which is a rational function. According to the classification of known foliations, polynomial foliations with first integral, this falls into the case L111. This is the terminology used by people who deal with foliations. It means that it has a first integral, which is a product of three linear factors with some powers. So it is of has a first integral of logarithmic type. It is so because you see the numerator is a reducible polynomial over C. But what is interesting that it's reducible in two different ways. So you have just the first way is just x squared plus y squared, and the second one, okay, it's slightly different. We shall see that it has an important consequences in what follows. So this is the brief history, some marking papers on this subject. The story began in the 60s with a paper of Laut, and then it was extensively studied from Ciccone, Carmen Ciccone and Mark Jacobs 30 years ago. In two big papers, they described the beginning of the perturbation theory of this differential system. But 10 years later, Ilie found a mistake, rather important mistake, because they counted limit cycles which can bifurcate from this system, and it turned out that there are some conceptual mistakes, not just because of computations. So he described bifurcation functions in full generality, but he omitted some details. We shall come back to this later. More recently, Cheng-Ji Li and Jean Melibre wrote a big paper, long paper, on exactly this system, when they used the fact that the system is isochronous and used the averaging theory to do the computation in some different way with respect to the papers, the preceding papers. They obtained results which agree with the previous results, but their theory is not completely, in the sense that they take only special perturbation which are linear in parameters. They take only one parameter, and moreover they stop at the second order. So we shall come back to this question later also. And I was interested in this problem because of some discussions with Jean-Pierre François. Maybe he is here. I didn't saw him here on. He told me that he will assist on this talk, but maybe he has some problem. And it turned out that it's much more interesting.
Oh, he's here.
Problem. Yeah, he's here.
He's here.
Okay, fine, thank you. It is much more interesting that one can suppose initially. So, what is our aim? The question which you ask is about the phase portrait of the system, which is close to this one, but which is still quadratic. So, we take arbitrary quadratic perturbations of this initial system. So, arbitrary. It is like in the paper of Iliev, although it is not quite clear from the paper itself. And you ask how many limit cycles. Initially, in fact, I was interested in the following challenge. It is known in the theory of quadratic vector fields that at most 4 limit cycles can appear. It is conjecture that it's a theorem, but it is never proved. Then it is also known that some configurations of limit cycles can appear. It means the following. Suppose that you have 2 nests of limit cycles. So, I mean, limit cycle should surround one singular point, but you may have two singular points surrounded by limit cycles. And this is different from the case when there is only one singular point surrounded. So what kind of combinations of limit cycles? It was never observed a 2-2 configuration. And in our system, you have 2 centers. So we hope that when you perturb a little bit, we can have some configuration, so like, say, 2 limit cycles around the first center and 1, or maybe 2-2. So if you find 2-2 combinations, 2-2 configuration, you shall be, okay, maybe not famous, but very well known, a respected guy, because so many years nobody found this. So I was just curious, why should you not, maybe it is possible indeed to have 2-2. And it turned out that this question is not studied. It was never studied in the literature for some reasons, except partially in the paper of Libre and Li. They claim that there is a, for instance, 2-1 configuration. But they did not claim that there is a 2-2. In fact, okay, at the end of the paper, we shall see that both of the claims are wrong. You cannot have neither 2-2 nor 2-1, which is, okay, a deception, but that is life. So this is a different kind of result. Maybe you shall try to see why this is true, why you cannot have so many limit cycles. So let us turn to the general quadratic perturbation to our quadratic vector field. You have, in fact, a lot of parameters. If you count the number of parameters of a quadratic vector field, you have 12. 12, it is a very big number. So you should have extensive computations, and you don't want to do this. We don't want to make long computation. I don't want, in fact. I prefer to make everything by hand. So you use the action of the affine group on the real plane. So you can make linear changes of variables and to take a quotient of the action of the affine group on the set of quadratic vector fields. But be careful, in any case, this action is not free in general.
Lubin,
Yeah.
excuse me, comparing to the Bautin's case of the perturbation of the genuine center without the quadratic term, you can get rid of the A capital because it can be absorbed in the coefficient 1 before Z square.
In fact, the computation of Bautin is local. It is not well understood that it is local. We shall, in 2 pages, we shall show how this computation is not complete, in which sense. In fact, the Bautin computation gives some polynomial ideal. And if you speak about polynomials, these are global objects. But still, this describes the center set only locally. So we shall come back to this. So actually, we use this normal form, which is the normal form of Bautin, because locally, in a neighborhood of our system, the action is free, locally only. So there is no problem to take this quotient. So this greatly reduces the number of parameters. And you have, according to Dulac, Captain, the ideal which describes the set of systems which has a center in a neighborhood of our system. So we shall speak now briefly about the Bautin ideal. What is the Bautin ideal? We know that, according to an old theorem of Hussein or Sati, that the set of all polynomial systems which have a more center is an algebraic variety. So he gives reference also.
No, this is Dulac.
Sorry?
This is Dulac.
It is not, in fact, it is not Dulac.
If you ask, I'll see this. Actually, I think it is Dulac, but anyway.
Okay, most of the people believe that it is Dulac, but it is not completely Dulac for the following reason. Dulac put the singular point at the origin always. Right? This is some technical restriction which seems to be obvious. If you have a foliation with a singular point, you can put it at the origin and fix it there. And you say, okay, this is just a translation. But it is not only just a translation. This means that you localize the problem. You shall study systems which are locally around your system. It can be even the linear center. Locally, which are close to this one and which also have a center. You find that this is an algebraic variety. But it is not the global problem that you studied. You studied a slightly different problem. Take all polynomial foliations. We don't fix singular point at some point. You don't fix. And you say, okay, let us take the subset of systems which have at least one center. You don't say even which center you take. Maybe you have 10 centers or many. You say at least one. And so this is an algebraic variety. So let us see here what is the difference. We have computed here this ideal for the 2 centers of this near our isochronous system. The first center gives some simple ideal which has 3 generators. So it is not 4 like in the Theorem of Captain Dulac. It is just 3 generators. Why? Because we take not a neighborhood of the linear center, but we take a neighborhood of just one special quadratic system, this isochronous system in the beginning, and you look at small perturbations and you say, okay, there are 5 parameters, lambda 1, 2, 3, 4, 5. And when these 3 generators of the first ideal are 0, then for sure our singular point is a center. But attention, this holds true for small lambda. Okay, you can say when you have polynomials there, global objects, of course you can do this. But let us see now the second center, because I said that you have two centers. What we see that the ideal is different, which is not surprising. Why should be the same? Let us see the geometric meaning of these two ideals. The first ideal describes has in fact the variety of the first ideal has two irreducible components. The first component corresponds to Lotka-Volterra type L111, and the second is systems which are pullback. They are usually called in the quadratic case reversible systems. If you look at the second center, you still have these reversible components, which is the same. The meaning of this is that the two centers are persistent in the irreducible components of systems with a center of type L12. The notion of persistence of centers was introduced to my knowledge by Linz-Neto, and at least it was studied in a paper 10 years ago by Linz-Neto, who proved some important results about basic results, I would say, about persistence of centers in the irreducible components of the center set. So when you have two centers, you expect that both of them are persistent, right? At least this should be the general situation. But if you looked at our two centers from the point of view of the L11 component, we see that they are not persistent. In fact, around the origin, the component is given by a plane, but the second center, which is not at the origin, is given by a different equation, which is not a plane, so it intersects the first one, and it is not the same. One would say, from the point of view of the Kapteyn-Dulac results, that we have two irreducible components in some sense. Okay, the second center is just translation of the first one. So if you translate the first to the second, you should translate in some sense, so not translate, but map the first set of equations to the second one. But still, these are like two irreducible components which are distinct. In fact, we know that globally, because of the theorem of Cousin, that globally we have just only one irreducible component. So what happens? Here is an attempt to describe what happens. So I pictured in this figure just the irreducible component L111. So this is a set of plane quadratic system which have first integral, which is given as a product of three linear terms with some powers. It's an irreducible component. And it turns out that it has a self-intersection. It is not at all as in the Dulac-Kapteyn theorem, when you have the Lotka-Volterra component is in fact a hyperplane, so it has no intersections. In fact, it is a global object which has a self-intersection, and it is even from the point of view of the moduli theory. If you take the quotient of the everything with respect to the affine group, you get some orbifold, and you take just the irreducible component inside, it will have still a self-intersection. So it is something fundamental for the for this component. You see how move the phase portrait. I picture the real phase portrait, and everything what is given here is real in a real domain. You see in the self-intersection point, you have two centers, because in fact generically you have only one center, but when you arrive at the intersection, you have one center plus one center for each local component. We have locally two irreducible components, but globally we have only one irreducible component. And one may ask, okay, how do you call these two centers, persistent or not persistent? It seems that in the definition of Linz-Neto, he did not consider such a possibility because you see each of these centers is either persistent or non-persistent. It depends on the direction of the deformation along the irreducible component. So you can speak about semi-persistent centers, which are related to the self-intersection. But it seems that, in any case, it seems that this phenomenon is new. It was not observed before. It is strange a little bit because the system is so classical. So the general problem is to describe the irreducible components of the center sets, but globally it is not done for sure, neither in Dulac, nor in Kapteyn, nor in Bautin. So let us continue with the perturbation theory, which was our initial motivation. What is perturbation theory? Okay, suppose that we know which are the centers of these systems when you deform. So you know very well the center set, you have described all this. But when you don't have a center, maybe you have limit cycles. The question is how many limit cycles when lambda small. So this is what we call perturbation theory. So the general problem is to describe the phase portrait for the deformed system. Of course, if possible, describe also the bifurcation diagram for which parameters we have this portrait, for which parameters we have another portrait. The general approach uses always the Bautin ideal. This is some specific situation which is related to the fact that our system is of infinite codimension. What does mean infinite codimension? Finite codimension, for instance, take a polynomial in one variable, say x squared. You know, when you perturb analytically this, we shall still have two zeros, two roots of these analytic functions close to zero. You say that the multiplicity of 0 is 2, or the codimension of this polynomial is 2 in the set of all analytic functions analytically. But what happens if you have a constant, or say the constant is 0? You shall have a 0 of infinite multiplicity in some sense, and so you expect to have some phenomenon in infinite codimension. So this is the same here. So what you do with such a situation? You just take the first return map, which can be defined in full generality, even if you don't fix the singular pointed origin. But the usual approach is that you fix. So let us fix. You take some cross-section to the set of orbits. You take the return map with local variable h. So if you have a fixed point, that is to say a limit cycle, for this return map, you shall have this identity P return map minus h is equal to 0. But as everything is analytic, you can develop, and remember that in your development, okay, if you have a center, everything is 0 because you have identity, so you can divide with respect to the ideal. So I skip here the technical problems around this division, the radius of convergence, etc. The important fact is that you have such a division of this displacement function, difference between the return map and the identity map. And let us take some simplified situation. Imagine that you have only one generator. Of course, we have 3 here, but imagine that you have 1. So in this case, we shall have some simplified equation, this one, some polynomial in lambda multiplied by something, some power series, which when lambda is 0 is not identically 0. you shall get some function. And it is like, okay, if you are interested in to count the zeros of this analytic function, the points when this function, sorry, is 0. So in this case, you can skip the, sorry, what happens? Okay, you can skip this V0 lambda, this factor. Sorry, my computer is doing something that I like, okay. And the important function which governs the 0 is phi 0. If you have a 0 of multiplicity 5, you shall have at most 5 zeros after deformation with respect to lambda. So this terminates the problem. So this is the problem is solved, 5 zeros, so 5 limit cycles. But this is only the case of one generator, that is to say, the ideal is principal. But now we know from the general theory that if you have an ideal which is not principal, in our case polynomial ideal, you can principalize this by making blocks. So the geometric side of the problem is the Hironaka theorem. In fact, we need some weaker statement just about the principalization of the ideal. So the important claim is that it is always possible by making some finite number of block-ups to achieve that locally we shall have an ideal which is principal. It means it is some ideal sheaf, in fact, on the exceptional divisor of the blow-up. And if you localize, that is a neighbor of any point, this ideal sheaf is principal. It has just only one generator. So ideologically, the situation is very similar to the situation when you have only one generator. And this fact has been extensively used since the very beginning of the bifurcation theory, although without theoretical justification. When I speak about beginning of the bifurcation theory, certainly it is in at least 70 years ago. Okay, so we see that the problem is, in fact, to find zeros of this function phi I when lambda is 0, and in fact some combinations, maybe arbitrarily linear combinations of them. So in our case, maybe the best is to try to compute them. And how do you compute these functions? You compute them by making use of the so-called Melnikov function. So instead of multi-parameter deformation, you take one parameter. That is to say, you take arc. You have some parameter space, some algebraic variety, and so to study this variety, you take arcs. So when you take arcs, you have arc space. So it was introduced by Nash, this way of studying singularities of algebraic varieties without doing desingularization in the sense of Hironaka. And so it is a little bit in the spirit of Nash. We shall take arcs. And what you obtain when you take arcs. So let us go to the previous page. You see this function vi lambda. What happens if on the place of lambda you put epsilon? Okay, it depends. It depends on the ideal. If you take a look at the ideal, you have linear terms and quadratic terms. Of course, if you replace lambda by epsilon, you shall have on the place of lambda 1, lambda 3 linear terms, on the place of lambda 2, lambda 5 quadratic terms. So the idea is to develop with respect to the small parameter the coefficient of epsilon power 1 will correspond to coefficients of lambda 1 and lambda 3, while the coefficients of epsilon square will correspond to the second term of the Boolean ideal. So in fact, by making use of such Melnikov functions, you can reconstruct the Boolean ideal, and even better, we can reconstruct the division in the Boolean ideal. Well, it is what we shall do in the next pages. So this is the general formula for this so-called Melnikov function. When you replace lambda by some power series in epsilon, okay, you shall make some, you obtain some asymptotic effect convergent development, and you hope by making use of some asymptotic theory to obtain the dominant term, this mk. This is called Melnikov function of order k, because it is multiplied by epsilon power k. Morally, it means that in this way you hope to study the homogeneous piece of degree k of the Boolean ideal. Fortunately enough for us, we shall stop only at the second degree, so there will be no long computations. So let us see what happens. Okay, see here I state some very general fact, which is not specific for our problem. And the general fact is the following. In fact, we want to study all possible Melnikov functions. It turns out, according to another general theorem, that in such a way we can bound effectively the number of zeros, so limit cycles. But geometrically, in fact, rather geometrically and algebraically, it can be traduced on a different language. We don't speak about Melnikov function and limit cycles, but you speak about exceptional divisor. Of what? Okay, we have an ideal. The variety of the ideal is singular. We are interested at the point 0, lambda equal to 0. Let us blow up the ideal in such a way that our ideal becomes locally principal. We shall show how this can be done. In this case, there is it's very remarkable, there is a bijection. That is to say, a one-to-one correspondence between all possible Melnikov functions and points on this exceptional divisor. It's a very remarkable description of the set of Melnikov functions. Of course, these Melnikov functions, if you look at the initial formula, are described only modulo multiplication by constant. So you mean modulo such a multiplication. There is an identification. So recall what is the definition of a blow up of an ideal. So we don't blow up a variety, but rather an algebraic object. It is just the following. Here is, for instance, the situation when you have 3 generators, ideal generated by 3 binomials. You just take the map which to lambda associates the point V1, V2, V3 projectivized. And so this is some graph of, you look at the graph of this map. It is of course not always defined, well defined, because when all the V are 0, of course this point is not defined. But let us consider the graph of this map where it is defined. It is defined in a complement to a Zariski subset of the parameter space. So it is well defined on a rather huge space. You take the Zariski closure, so you get some curious surface, which is called blow up of the ideal. All this construction is called blow-up of the ideal. And the main property of this blow-up is that the corresponding ideal, which is rather the pullback of the ideal on this surface, is locally principal. That is to say, it defines a sheaf of ideals which are principal. And really like very much in this situation when the ideal is principal, because we can say immediately what is the maximal number of zeros of the function which we are interested in. Moreover, we can exactly say which kind of Melnikov functions can appear, because there is a bijective correspondence with this exceptional divisor. But let us continue, and let us take a look at the homogeneous piece of order 1 of our Bautin ideal. This can be useful in the situations in which we don't know, in fact, explicitly the generators of the Bautin ideal, but in such a way we can compute easily just the homogeneous part, which is generically will be the tangent space, in fact, to the variety of centers. So, as the first integral is rather simple, we get by standard computations, which are classical, an explicit formula for the first Melnikov function, which is some abelian integral along the level set of this first integral, but it is immediately seen if you make a picture of this level set, that this level set is in fact a circle. Circle is something very simple. Indeed, it is okay for something simpler than that is only a line. So you have circles. So geometrically, these are Riemann spheres. So Riemann surfaces of genus 0, but they shall have some punctures. So spheres with punctures. Punctures, for instance, here we have a division with 2y minus 1, so there is a denominator. This corresponds to punctures, so you can remove 2 points, and you have at infinity also 2 points. So it will be a sphere with 4 removed points. On this sphere we have this abelian integral. So every such abelian integral is in fact a residue, or sum of residues. So there is no problem to compute it explicitly. So let us compute explicitly this. And the next page, you see what we obtain: some linear combination of, with respect to h, more or less of degree 1, in fact. Okay, 2, because everything is multiplied by h, but it is some h which is not very important. This corresponds to the 0, to the fixed point, which is the singular point itself. So the situation is extremely simple. The conclusion is only one limit cycle can bifurcate, result obtained already by Ciccone and Jacob many years ago. Let us turn out now. Let us take a look at the second Melnikov function. So, curiously enough, this second Melnikov function is an iterated integral. It turns out that it's a general phenomenon. The third one will be an iterated integral of length 3. So it is a good occasion to familiarize with this object, iterated integrals. So there is a general formula for iterated integrals which appear in this context. If you use this general formula, we get this, and 2 is, here is the definition of our integral. What is iterated integral? It is just integral of integral. So you iterate the integration. By Fubini theorem, you hope to be able to compute this, but it's not so simple. From the general theory, we know that our integral depends not on the homology class of delta. If it was only on the homology class, it will be some sum of residues, as in the preceding case. But here, it depends on the homotopy class. What is curious, and it is indeed a challenging problem, to compute explicitly M2, but making use of standard procedures, for instance, the algorithmic procedure introduced by Francois, or by the deformation methods introduced earlier by Jolondek. It is more difficult that it might okay, personally, I was very surprised that it's so difficult to make a direct computation. Jean-Pierre Francois probably already succeeded to do this, but it took him more than a month, I think. Okay, but in any case, it is possible to compute not by direct methods, but just by making use of monodromy properties of this M2, this Melnikov function, and the final result is very simple. This very simple formula that you see here. I would like to discuss just a little bit how do you obtain such a formula. One approach, this is the approach that we suggest, is to use the monodromy properties of the Melnikov function. So monodromy properties will be, this is something very general. If you have any problem, bifurcation problem of this type, you can always ask about monodromy properties. So what is the monodromy? You have analytic function which lives on a plane. We can infinitely continue this function. We can get analytic continuation. How many analytic continuation, how many branches this function can have? As the situation is simple, it can be maybe more clear than in the most general case. So what we have to do is the following from a geometric point of view. Instead of studying analytic continuation of analytic function, we shall study analytic continuation of a homotopy class of loops. So the situation is pictured here. So just to explain what I picture, I shall come back to the preceding page and to recall that we deal with a sphere. Sphere, it is the same as a plane from complex point of view. I mean, the complex plane, it is just a sphere with removed one point. So if you have a sphere with removed 4 points, it is the same as a plane with removed 3 points. It is enough just to take an uniformizing variable, as we do it here, z equal to x plus, you see the formula, and you get a plane, and we shall traduce the study of our analytic function as a function on this plane. So this function is, in fact, it's a period. Here what we see on the figure, these are 4 different figures, in fact, 4 planes. In each plane, we have 3 removed points. The first figure is at the beginning, we have 3 removed points, which corresponds to the 4 removed points before. Of course, there is 1 removed point in infinity. And the rules of the game are that the difference between the points which corresponds to alpha and beta is a constant, which is not 0 and which does not depend on h. Otherwise, the points are arbitrary. Further, in this situation, the fundamental group is free with 3 generators. We call them alpha, beta, gamma. They are pictured. These are small loops around the 3 removed points. Fairly simple situation. And our loop is the composition of beta and gamma, as it is shown on the second picture. And now the game is, okay, if you deform alpha, beta, gamma in an arbitrary way, how many homotopy classes and which one, you have to describe them, you can obtain. If you can give a good answer to this problem, you shall give an answer to the problem how to get all analytic continuation of our function. So it turns out that the appropriate algebraic object here is the what we call homology of the orbit. This definition was introduced maybe by me maybe 15 years ago, but more recently Sergei Novikov with collaborators with Mardeshich used in a very interesting way this definition, and he proposed a new name for this homology, to call it homology of the orbit. This is a name that I like very much. So what is the homology of the orbit? So this is an algebraic object. Here is the formal definition. I'll explain what is what. So O delta, it is the orbit of our loop in the fundamental group of our plane with 3 removed points. So it is some set in principle, but we take the least normal subgroup which contains this set. This is the orbit. So it is some subgroup, normal subgroup of the fundamental group. And we take a quotient. Quotient with respect to what? With respect to its kind of abelianization of this orbit, but apart very specific one, we take just commutators between elements of this orbit and all other homotopy classes. In fact, it is purely algebraic. You can think about arbitrary group, not especially P1, and some subgroup. To this pair, group and subgroup, normal subgroup, we can associate some abelian group, which construct in this way. We take the subgroup, which here is O, and we factorize with respect to commutators. That is to say, with respect to the commutator group, subgroup, which is generated by commutator. What's a commutator? A commutator, I hope that you know what is it, but here is the definition of two loops. This is A, call them A and B, or two letters, two elements of a free group, A power minus 1, B power minus 1, AB. Of course, if the group is commutative, it will give the identity element. Okay, so there is one example that everybody knows. If you have a fundamental group, that is to say, if you have an orbit which is equal to everything, that is to say equal to the fundamental group, you just take the definition of the usual homology of the Riemann surface. Okay, this is in the example that you see. So we are interested in this homology for the following reason. There is a theorem, general theorem, which I state here, which says that the monodromy representation in fact is a sub-representation of the standard representation of the fundamental group of the base of base. It is H, the parameter H represented on this abelian group H1. Now I mean the following: take arbitrary loop, arbitrary homotopy class in P1, we can do analytic continuation of this. So this with respect to H, there is a deformation parameter. So you have this generates a representation of the fundamental group of C minus the singular values of our function H, big H, first integral, into the automorphisms of this orbit, the homology of this orbit. So this is something very general. This is the case for any Melnikov function of any order, for any deformation problem of infinite codimension when you can construct such Melnikov function. So the key observation is that if you geometrically understand this representation, we shall understand also our representation of the monodromy representation of the Melnikov function. So fortunately for us, maybe not so surprising, as we have a very simple situation, a free group with 3 generators. We have some subgroup and we have the homology of this subgroup. Okay, it turns out that it is finitely generated and it is free, and moreover there is no torsion. So it is the simplest possible situation. This homology is a dimension 2 in the sense has 2 generators without relation, so free group without torsion, and moreover it is abelian by construction. So this is some element of proof which contains in fact a little bit hidden the Picard-Lefschetz formula for such loops. In fact, here in this picture we can see the Picard-Lefschetz formula. This situation, so we have some loop beta gamma and you have alpha, which makes one turn around one puncture. So what happens? Okay, beta gamma is transformed like in the last picture, and if you follow well the path, you see that the effect is if you conjugate gamma by alpha. So this is the Picard-Lefschetz for if I like to call it Picard-Lefschetz. We shall see just below because it's a Picard-Lefschetz type. So this is the monodromy transformation, but from this point it is not at all clear what is the orbit. Only after computation it turns out that the orbit and the quotient with respect to this ability, to this commutator subgroup is finitely generated. Curiously enough, it seems that the general case is not this. The general case is when this homology has infinite number of generators. So the situation is the following: we have at the beginning free finitely generated group. You take some orbit inside which is a subgroup. After computing this quotient, we take some abelian group. This abelian group is not finitely generated. It was conjectured, it was a question what was asked some years ago, more than 10 years. Is it possible to prove that always you shall have finitely many generators? It was proved by Novikov, Mardesic, and Alvarez Bravo, I think. I'm not sure. That okay, it was shown that there are examples when the generators are infinitely many. In fact, and can be shown that this is rather the general situation. It is not particular situation. So if you have something homology of dimension 2, the things are much more transparent. These coefficients here before the logarithm can be computed from the monodromy properties. We shall have only one singular point for this function, which is easy to check. So what is the monodromy of this function when you make one turn around h equal to 1, for instance, here? The monodromy should be some coefficients which is just it has the same form as the original function, but the difference is that you don't integrate with respect to delta, but you integrate to alpha beta. In fact, the reason is the following, that in the homology, the monodromy of delta is like this. Delta is transformed to delta plus commutator. And here beta means Greek beta. It's a mistake. So Greek small loop around a puncture. And this is the coefficient before the logarithm. This is the result of the general theory. Now, by Fubini theorem, you can prove a formula, nice formula, general formula iterated integrals of length 2 along commutators. It is the formula says that it's a determinant of periods, usual periods, which are computed by Cauchy theorem as residues, and you get lambda 2, lambda 5. So the guess is that lambda 2, lambda 5 is a term which appears in the Bottin ideal. So this is the way in which you can guess the Bottin ideal. Of course, we know in this case because of the Dulac result, the Captain Dulac result. But around the second center, it was not known. This is in fact indeed the way in which I guessed the second ideal in the same coordinates as the first one. Okay, it remains some function to compute here, p, but I don't compute it here because, okay, you should notice that there is some piece, some big piece of beautiful theory beside, which is hidden behind these straightforward computations, and this theory should work in general for other situations when you have Melnikov functions. So let us, I am close to the end of my talk. So let us, just before the end, to come back to my initial question was, in fact, how many limit cycles? Okay, we have some theory, some pieces of theory, but the initial question was, when you perturb, how many limit cycles you can obtain from the two centers, not only from the first centers. Moreover, simultaneously. So this is the point, the word simultaneous. Because if you study separately each center, you shall know how many centers you can obtain from the first one, from the second one. The answer is classically known since Iliev, a paper of Iliev, and he corrected the proof of Chikon and Jacob. It is known the answer is 2. Okay, each center has 2 at most. But is it possible to have 2 plus 2? If you can prove that you have 2 plus 2, it would be a famous theorem because nobody has seen a 2-2 configuration in quadratic systems. And quadratic systems, you know, for people who deal with such kind of polynomial system is exactly the same as elliptic curves for people who deal with some hard problems in algebraic geometry. So the elliptic curves here, they correspond in a sense to the quadratic system, which at the first sight very easy to deal, but in fact not so easy. A certain part of the truth in the general case is hidden here in the quadratic case. So to study simultaneously the two centers, you have to repeat all this theory, but simultaneously to repeat. It means what? It means that you should do the same for the two centers, but with the same coordinates at the same time. It's forbidden to translate one center to the other. You have to do with the same coordinates. And for instance, to compute all pairs, simultaneous pairs of Melnikov function, you have to blow up but two ideals simultaneously. So what is a simultaneous blow up? Okay, it is the following object. You take the graph of this map, which looks like the graph of the map before, but it is simultaneous. We have the image is not in P2, but in P2 times P2. Okay, so it's a map. It is not always defined, but we just take it where it is defined. You take the closure of the graph of this map, the Zariski closure, and then you can speak about the pre-image of the origin. It will be some complicated algebraic surface. The dimension is not clear in principle. We hope I hope at the beginning the dimension will be 3, something as dimension 3, but it is not of dimension 3, it's of dimension 2. If it was of dimension 3, it is possible to prove that you can have 4 limit cycles, but dimension 2 Okay, in fact, it can be described very explicitly. What is dimension 2? Which it turns out that there are 3 irreducible components. It is possible to describe the pairs of Melnikov functions which corresponds to each point of this exceptional divisor. As we know that these functions are very simple, we saw these examples as either polynomials or logarithmic functions, it is possible very precisely to compute the zeros of these functions. And the answer is, okay, in the last page of my talk, here is the theorem. The theorem is, in a sense, a deception, because we hope to get 4 limit cycles globally, but we take only 2. So all configurations are possible. So it means 1, 1, 2, 0, 0, 2, 0, 1. But the sum is at most 2, and this corrected a mistake in the previous paper of Libre and changes. So here, this is, you see the tradition in this field is there is a long line of mistakes. So each paper is corrects mistakes of previous ones. We maybe, you know, the story of the 16-killer problem. It's like this. So I think that I shall stop here. Well, thank you very much for the attention.
Okay, so let's clap. So, any questions? Well, first let me make my question. Lubomir, there is this orbital homology which is developed, but how about the differential equation of M2? In this case, is it possible to write it explicitly, like the equation?
It is the general theorem says that the Melnikov function of any order satisfies a Fuchs type of equation, differential equation, which in fact it is more correct to call it of Picard-Fuchs type, although the solutions are iterated integrals. And for your question, the answer is simple. It satisfies a second order, Picard-Fuchs equation which has 2 solutions. The first solution is some polynomial of small degree 2, and the second solution is this logarithmic function plus something. And the monodromy is just like in Picard-Lefschetz formula, but the solutions, to my knowledge, not abelian integral in the classical sense. Maybe it is interesting to look at the monodromy. So this is the situation. It is a second order. In fact, it was computed by Iliev earlier, this equation, but Iliev, he didn't use neither iterated integral. It was not known even that Melnikov functions are iterated integral. He used a very strange procedure by hand, by deformation. It means like something like this. He deformed a little bit his problem to some generic integrable system. For the generic integrable system, you compute the first Melnikov function, which is, there is some explicit formula, analytic formula, and then he develops this function with respect to different deformation parameters. Very hard job analytically to do this. And when you take back these parameters tend to 0, you take some coefficient and you claim this is your second Melnikov function. Okay, in this way you can compute the second Melnikov function by some deformation argument. But in a similar way, we can compute a differential equation. He says, okay, the first Melnikov function in a generic case satisfies some kind of differential relations, which are not closed in the sense that they don't form a differential equation. We can say that it satisfies a differential equation of infinite dimension, something like this, which is no idea how to use its properties. But what is curious that you can take the limit And he did this. He did did a very tough computation. I think that nobody understands how he succeeded to do this. And at the limit, he gets a mysterious differential equation. And now it turns out that okay, it's very easy to compute now this differential equation with you say just that the orbit is of dimension 2. So if the orbit is of dimension 2 of your period, so it satisfies a second order differential equation. So it's a basic fact. So it makes clear a little bit more why he obtained the second order. So.
Okay. No more question, Sergey? You don't have any question? Maybe. Okay. So if there is no question, let's officially finish the. Thanks again, Lubomir, for giving this talk. So once again.
Thank you.
Okay, thank you. Let's stop recording.